Welcome to part 4 of the VisPy Realtime Data video series. In the last video, we left off making a timer trigger some data generation, and we showed at the very end how that might not work for all use cases, specifically when data generation takes a long time. This could be from waiting for your data source, whatever's providing the data to your application, or the calculations that you're doing to generate the data yourself. In this video, we're going to focus on one other way of generating data, one other way of communicating with our data generation. If you look very closely at the VisPy gallery website, you'll notice that the script names for part 3, 4, and 5 are actually named example 3A, 3B, and 3C. That's because these three different example scripts all show the same high-level application. They're showing data that is updating from some synthetic data source. They're just communicating with that data source in a different way. So where the last part 3 or part 3A, was using queue timers, we are using threads in this video. So just to drive home the issues that we ran into last time, if I take the code that we had from part 3, I uncomment this time.sleep 5 seconds, and I run the example, we'll notice that every 5 seconds, the data is being updated. We get a new point in our line plot. We get a column change and the random data change in our image. But we have the problem that even though I've clicked on this drop-down menu, it's taking multiple iterations of the data generation to actually update the visual or update the application. So let's look at some slides to demonstrate why this is happening and how we're going to change things in this video. So this is what we originally had in part 2. We had two combo boxes for our color map and line color, and they're using Qt signals and slots to update the canvas wrapper, or specifically the image visual and line visual of that canvas wrapper. In part 3, we added a timer and a data source. The timer would trigger every some number of seconds and would call the complex data generation function. This function would then emit a signal to tell the canvas wrapper to update the image in line with new data. In the most simple way of explaining it in this video, we're essentially going to tell the data source to just keep running. Instead of being called once for every iteration, we're going to let it run a for loop or a while loop or some type of continuous loop where it will run in its own thread and update the GUI, the visualization, as it continues processing. If we think about what this looks like on the event loop, we talked about most GUI frameworks, including Qt, which we're using here, have a GUI event loop. In our current application, what we have is a single thread event loop represented by this red arrow, where Qt, the red arrow, will go through a series of events, and as things happen, it'll keep processing these events. New events may come onto this queue, onto this event loop, and it'll just keep processing and keep going, and that's how you get interaction and interactivity in your application. We pointed out that in the current version of our code, a timer event shows up on this event loop just like any other. But if it takes more time, as I just showed with adding that 5 seconds of sleep, we can't, or Qt can't, continue on to more events. So we get this this lag, this break in user experience as we wait for the event loop to catch up. The solution that we're going to work on in this video is to split these two tasks into separate threads. So on the right here, we have the GUI main thread. This is going to handle everything that has to do with the GUI. So drawing, key presses, mouse events, things that are the user directly interacting with the GUI or the GUI wanting to display something to the user. On the left, we're going to put all of our data generation. In this example, we're not going to use timers anymore. We're just going to let the data generation run its code continuously. It's going to keep emitting new data. The way it's going to do this is with Qt signals. So because we're using Qt signals, Qt handles all of the inter-thread communication for us. So if the background thread, for example, has new data that it wants to give to the GUI thread, it can do that. If the GUI thread had some modification that it wanted to apply to the data generation, we could use signals, and Qt would handle everything, all the complexity with passing that information between threads. I should note that one limitation of this kind of idea, or handling events in one background thread versus the GUI thread, is that all draw events, anything that happens with the display, have to be done in the GUI thread. What this means is that you can't modify a VisPy visual in the background thread. So we're going to limit ourselves in the background thread in this example to generating the NumPy arrays or the dictionary that has our NumPy arrays, and we're going to give that to the GUI thread. So all the GUI thread has to do is update the visual with that new data. So if we go back to this diagram of showing that our data source is continuously looping, it's calling itself or always processing new data, always producing new data, emitting it as a signal. What we aren't showing in that slide is the threading. And while the threading gives us a lot in that we can do a lot of background data processing without interfering with the GUI loop, it does add a lot of complexity as far as getting our data source to be in a background thread and communicate with that background thread when things need to shut down, or when things need to start, or when things go wrong. So even this diagram is a simple version of this type of communication, but it points out the basic layout that we're going to have in our code. We're going to create a QThread object, so that's something that Qt gives us, that is a handle or a proxy to an actual low-level thread instance. At the same time, we will create this data source that we've already created with a few modifications, and we're going to tell the thread to run our data source in the background thread. The way we do that is with a couple different function calls, but primarily we're going to use signals and slots to have the thread tell the data source, the thread is ready, it's running, you can now generate data in the thread. If the data source is done, we could optionally close or kill the thread so it stops running. In that case, we could have another signal from the data source communicating or emitting that information to the thread handle. And there's a couple other signals that we'll see as we start modifying the code. So let's dive into the code and see what has to be done. So the first thing we're going to start doing is laying out all of the complexity that is involved with setting up these threads. This way we should be able to see what other modifications we have to make to our code so that everything works and plays well together. The first thing we're going to do is create a thread handle that I talked about. Inside Qt core, we have a QThread object. Like all Q objects, this can have a parent to define some kind of hierarchy so that if a parent needs to close or be destroyed in some way, that the children know that they also need to be destroyed. So we're going to tell our thread that it's a parent of the main window. What this should allow us to do is set up the thread to destroy itself if we close our main window. And this hierarchy, this parent-child relationship, just kind of helps solidify that. I'm going to move the data source creation that we had from before down here. And then what we want to do is a fancy little Qt method call that's on all Q objects, which is called move to thread. And we're going to give it the handle to our thread, our data thread object. So what this says is that this data source object, this Q object data source, no longer belongs to the main GUI thread. This means that all of the event loop stuff, everything else, that is meant to happen in that background thread that the data thread object is a wrapper of, it is a proxy to. In this next block of code, we're going to do a lot of connections between different signals. If you were to research this topic yourself, you would find a lot of different examples of using different signals connecting to different functions or doing things in different ways. This is the way that I use it, and this is the way I've gotten it to work, and the way it works for me. And I'll try to explain every connection that I make, so hopefully you can decide for yourself whether this is the right choice for your own application. So the first signal is actually one we already connected, is this new data, connect it to the canvas wrapper to update all the data, to update our visuals. That doesn't change. Next one we're going to create is data thread started. So started is a signal that comes with the QThread object. This says the thread has started running, it's ready to process, it's ready to execute functions and commands and whatever. We're going to connect this to our data source, and we're going to connect it to the run data creation method. So this is the one that was called a single time for every timer interval. We're going to change that coming up so that it does a for loop and it just continues processing without having to be called multiple times. Speaking of timers, we can get rid of the timer that we created in the previous example. We're not going to use that anymore. Next, we're going to connect a new finish signal on our data source to our data thread, specifically the quit method. What this means is we're going to emit this finish signal when our data source has generated all the data that it's supposed to generate. You could imagine this if you were listening to some remote connection, some internet, or some instrument that was generating data, and you got some kind of event that said there's no more data that's going to be generated. There's no more reason to generate anything else. So we can try to save some resources or clean things up early by having our data source tell our thread to quit. One complication to this is that we need to add a special argument to this connection to define this signal to slot connection as a direct connection. This kind of breaks the separation of GUI thread to background thread, and we'll do this one more time for another signal. Because our data generation will be a continuous loop, there's no interrupting it. Similar to in our timer example where the timer ran for a long time and it stopped the event loop from continuing, these signals and slot emissions or connections are also part of that event loop. So if our for loop can't be interrupted, then we need to use a direct connection to tell Qt. It tells Qt to run this signal or run the slot that this signal is connected to in the thread that it was called in. This kind of gets around some of that awkwardness of trying to run a for loop in an event loop without it being interruptible. And hopefully this will make sense as we start writing the code and we see where these signals get used. So the next one we're going to do is we're going to take our window, and there's actually a closing signal that comes from Qt whenever this window is about to close. And we're going to connect it to a stop data method on our data source. So this is kind of a way of cleaning up our data source when our window is closed. Previously, because our timer was playing well as it could, with the GUI event loop, when the window was closing, there was no more data generation because there were no more timer events. Now that we have a background thread, our data source could keep generating data, could keep running, even though the main GUI thread is trying to close and is completely stopped. So here we're telling our data source to stop directly when the window is closing. We're going to use the same direct connection idea. This way, the main GUI thread is able to call this stop data method from the GUI thread, interrupting or working around the data source continuously running in its own for loop. Lastly, we're going to connect the thread's finish signal, another one that comes from Qt directly, and we're going to connect it to the data source's delete later method. This is one that is provided by Qt, the delete later. This says that when the data thread, the thread object, the thread execution is being destroyed, is stopping, is ending, that the data source that lives in that thread space, the data source object that we moved to that thread up here, we want to have Qt actually delete that. If we didn't do this and we had some kind of long running process, my understanding is that the data source would continue to live in this in the thread's memory space and would not be cleaned up. So this is one way to make sure that that happens. Okay, so those are all the signals that we're going to connect, and we'll create all of the methods that we connected to that don't exist yet. But before we do that, we're going to do a couple things with the thread. After we show the window, we're going to tell the thread to start. This will tell Qt at a low level to create a new system thread and start letting it execute. This should, shortly after this method runs, emit this data thread started signal so that data generation can start going. As you may remember, this app.run starts the main GUI event loop. So that starts that red arrow in my diagram processing events, and it just keeps going. When you close your GUI window, this function will actually return. And what we're going to do is make sure that our data generation completely stopped by waiting 5,000 milliseconds or 5 seconds for anything that's in the thread to stop processing and to have the thread actually destroy and stop processing. Just so we know when this is happening, I'm going to put a print statement here. So this way we just know that the window is closed and we are just waiting for the thread. Okay, so this is all of the complex, pretty much boilerplate code that we need to create a thread and then have an object run in that thread. Now we need to update our data generation so that it has all these methods that we're calling and generates data in the way this code expects. Okay, first thing I'm going to do is create the finished signal that we used. So this was the one that said this data source has no more data to generate, and we connected it to the thread to tell it to kill off the thread and start destroying any resources that it was using before. We're going to keep track of one additional thing here. We're going to have a Boolean flag that says whether or not this data source should stop generating data. This isn't dependent on the remote thing that we're getting data from. This is when the GUI window closes and tells us to stop generating data. This will be a Boolean flag that will update from a new method. I'm going to get rid of the count instance variable because we're not going to use it. We're going to change the data generation so that it runs as a for loop. So now that we're not using timers anymore, we don't need the timer event argument. I'm going to add a print statement here because now that we're continuously running, I want some basic indication that we are in the steps of data creation that I think we're in. And instead of, like I said, keeping track of a count, we're just going to run a for loop. So we're going to run a for loop for a number of iterations. We're going to, first thing we're going to do inside this iteration is check that new should end Boolean flag. And if we should end, we're going to do a little print. And then we're going to break out of this for loop. This should stop all of the processing and break us out of this for loop. We're going to put in here a really small sleep, a sleep of 1 second. We'll add a longer sleep later on when we're testing to make sure that these things are happening in separate threads. I also just noticed I'm missing a colon. But this kind of mimics what you might see from delay of talking to some remote resource or just data generation that takes a longer time. Okay, we're going to update our calls to our data generation methods. And instead of using the instance property that no longer exists, we're going to pass our for loop variable count. We have the same data. We don't need to update a count variable anymore. And then we want to create our dictionary as we did before and emit a new signal. So this takes care of our for loop. We're generating a new piece of data every time we're in this for loop. What we need to handle is the case where we're breaking out of this for loop or we've done all of the iterations that we want to do. And what that represents is that the data source is finished. There's no more data to be generated, or we were told that data generation should stop. So we're going to print a little message saying data source is finished. And then this is where we finally use our new finish signal to say, yep, the data source is done. Okay, lastly, for the data source, we need to add a new method that we connected to called stop data. I'm going to add another print statement just as a notification. Saying the data source is quitting. Somebody told us to stop. The way we connected our signals, that means the main GUI window will tell us to stop when it's closing. And we're going to, in this method, the only thing we're going to do is set should end instance property to true. So if we think about what the life cycle of this data source is, once the background thread tells us that we can generate, it will call this method. We will continuously run through this for loop. And if we reach the end, then we will emit the finish signal. This finish signal should tell the thread to quit and all the resources should be cleaned up. If the user closes the GUI window for whatever reason, even though our processing is going through this for loop, we used a direct connection, so that should set the should end property to true. And that means on the next iteration of our data generation, we should catch that change here, break out of the for loop, and again emit the finish signal down here after we've broken out of the for loop. So that is everything for the data generation change. Let's see what happens when we run this code. We forgot to create one more thing. On the main window, the closing signal is something I actually need to create. Okay, so now that we're at the MyMainWindow class, we can create a new signal just like we did with all the others called closing. And then we're going to create a new method called close event. This is actually something that Qt handles in a special way. So this is needed because as far as my research tells me, there's no signal that comes built into Qt to tell us that the window is closing. This is the best way that I could find to do it. Without this, we don't know that the window is closing, and we can't clean up the resources in other spots of our application. For some applications, this may not be an issue depending on how you design it and what you're expecting of the user as far as starting things and stopping things and what kind of background threads you might need. In this basic example, because we're starting a thread right away, the window and the background processing are really two separate things, and we're just communicating between them. So we need this close event and this closing signal to let that separate background thread know what's going on with the main GUI and what the user's intentions are. So we're going to print that we're closing the main window, and we're going to emit this signal. And then lastly, I'm calling the upstream or the Qt version of this close event so that if Qt was going to do anything else with this close event, it can go on and do those things. I just wanted to use this method here to emit that closing signal so that I can communicate with the rest of the application, specifically that background thread. So let's try running this again, see what happens. Okay. So this is our data generation here. This still has that 1 second sleep on it. So we can see some of the columns on the left of the image are turning to a solid color. We have the random data updating. We have the data here of our line plot updating. And then what's nice is that my drop-down menus are reacting immediately. So that shows us that everything with our data generation taking a second, we're not being interrupted. Let's really prove that by increasing the amount of time that the data generation takes. Before we do that, I want to point out the output here that we had updating messages saying that things were updating. We got the message that the window was closing. That's that close event in the main window. That communicated to the data source that it should stop. Then we got a message telling us that we're waiting for the data source to close. The data source said that it saw the signal to stop, that should end Boolean flag, and then it actually finished, and our thread was able to wait successfully for everything running in its event loop to end. So let's go back to the data generation and this sleep that we have here. Let's get rid of this 5 second sleep and put it up here. So we're just going to tell this sleep to take a long time. Let's try running this again. So now our data should generate much more slowly, but my color maps are still, or my drop-down menus are still reacting immediately as fast as they can, even while data generation is taking its time in this background thread. So compared to our previous example, this is a much better user experience, gives us much more flexibility as far as what we're able to do in that background thread. I've given examples in the past of communicating with a TCP socket. Maybe you're downloading large amounts of data from somewhere out on the internet. Maybe you're just running some heavy calculation that needs a lot of time to generate new data. Either way, the new data is emitted in the same way to the visuals. None of the VisPy stuff has changed here. We're all updating that in the same way. We've really only added the complexity of dealing with QThreads and communicating and making sure that all of our resources are released and cleared when things are done. So as one last thing, let's see what happens when we comment out the sleep and run this as fast as we can. That actually ran so fast that I couldn't get it into the window before it disappeared. Okay, let's try changing that sleep to a little slower so we can actually see it. So I'm still able to interact with this GUI perfectly fast, even when the data is being updated faster. Let's go even faster. Okay, the number of iterations for our data generation has been hit. What we can see in the output is we were updating data, and the print messages are a little out of order, but the data source said it was finished. So now what we see is that the main window was closing, waiting for the data source to close gracefully. That is our message to say that the thread is waiting for the data source, but since the data source was already closed, it returned immediately and our program was exited. So that ends our part 4 video of this series, our example 3B in the VisPy gallery. As a quick summary of what we did, let's go back to the slides and look at what we put together. So from a high level point of view, we took our data source and we told it to run a continuous loop. From that loop, it kept emitting data to our image and line visual. Because they were the main window and our data source were in separate threads, the event loops were kept apart, and whatever our data generation needed to do did not affect the way our user interacted with our GUI. It did not affect anything that our main GUI event loop needed to work on. From a slightly lower point of view, our data source is still emitting that data, but we had a QThread object managing a lower level system thread underneath, and we used a lot of Qt signals to communicate between these two and with our main window to make sure that everything was in sync. When things were closing, everything else knew that it needed to clean up its resources and stop generating new data, and everything could be cleaned up nicely and not hold up the user when the user wanted to close the application. So this ends video 4. In the next video, we're going to look at combining the last 2 videos where we use timers and we use threads, but what if we use the idea of timers or events inside a background thread, kind of the best of both worlds. We still have some of the complexity, but hopefully a little cleaner. So with that, I'll see you in the next one. Please leave any feedback in the comments below. If you find any issues with this type of thing, or you have any suggestions for better ways that QThreads could be used, please create an issue on the VisPy GitHub repository. There's a link in the description down below. Thanks.